Hello, everybody. Yeah, I am good day to you all. So this is week two. Week two lecture slides. Week two lecture slides. All right. So we are looking at describing data with numerical measures. Describing data with numerical measures. So you will always get data to work on. Okay. But what can you do with data? You have to be able to do something with it. So in week one, we look at describing data with graphs. Week one was on describing data with graphs. And week two is describing data with numerical measures. That's week two. Okay, there are, when you have a set of numbers, there are different kind of measures, arithmetic measures that you can use on them. One of them is measures of centers. Measures of centers, okay? Now, which is a measure along the horizontal axis that locate the center of the distribution. If you have frequency, how many times something occurs? 4, 5, 6, 7, 8. So here, this is 2. This is 4, Now, along horizontal axis here, trying to locate this middle point is a measure of center. It's done along x-axis, okay? Remember, when you have a table, of observation, how many times does x occurs? Maybe this one occurs 2 times. 5 occurs 3 times. 7 occurs 4 times. 8 occurs 9 times. 10 occurs 6 times. Now, this is the actual data. The F here is the frequency. Now, if you want to plot this graph, the actual data will be on your horizontal axis and the frequency will be on the y-axis. So you have 4, 6, you have 4, 5, 7, 8, 10. Okay, those are the actual data. So how many times does 4 occurs? 4 occurs 2 times. This is number 2, so this is 4. I'm just making this up. 5 occurs 3 times. So this is 5. See? 3 or 5. We do the same thing for 7 and so on and so forth. Okay? Now, let's have a table here. The birth weight data presented in the following table range from a low value of 5.6 lb to 9.4. Okay, I want to be sure this is being recorded. Yeah. So now, this is the table. This data is not your problem. You will get it from somewhere. It must be given. It must be given. Now, if you represent them, this data set with histogram, this is what you get. Representing this data with histogram, this is what you get. Now, the smallest of this data is 5.6, and the largest is 9.4. So your data will be between 5.6 and 9 something. Now, the histogram the one that has highest frequency is 7 point something, which is here. The frequency is 8. The frequency is 8. See that? The frequency of this one here is 5. The frequency of this is 2. Okay? This is representing data with a graph. Now, look at it again. The actual data, which is the birth weight, is on the horizontal axis. And this is a center measure. Okay? Now, you understand the reason why we have to talk about center measures. You want to know the average weight of babies that are born. Okay? So we count 7 point something across, like how many times you have 7.1, 2, 3. Yeah. Yeah. So sorry. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So you see that 7 point something occurs about 8 times. About 8 times. Let me clean it properly, please. Yeah. Okay. So once again, the values on x-axis, frequency on. Now you will ask me, where is this 30 from? You know, the frequency of each of the data points, when you add them together, is 30. So if x1 occurs 4 times and the total frequency for every values here is 30, then the relative frequency of x1 is 4 divided by 30. So this is a relative frequency. Okay. All right. Now, the first measure of center that we are talking about here is the mean. Is the mean. Remember, the entire, if you are looking at UVA-wise as a whole, UVA-wise as a data collection, you call this population. That's a big set. But if you are looking at only math and computer science department, that's your sample. So if I'm collecting all the age of students in the entire UVA-wise, that is called population sample. UVA-wise can be regarded as what? Population sample. I mean population. Now, population, sorry. Mathematics and computer science is just one of the departments in UVA-wise. It's a subset of population. So you can call that sample. Okay, so sample. So we are talking about 2 sources of information now: sample data and population data. Look at that. So now, when you normally, if you want to compute a mean of a set, if you have a set given as 3, 4, 5, so there are 3 numbers here. This is your x1, this is x2, this is x3. There are 3 numbers here. So the mean is actually when you add everything together and divide them by the number, this by 3, because there are 3 numbers here. And that will give you 12/3, which is 6. Okay, but if you are computing the mean from a sample, you write it as x bar. If you are computing the mean from a population, you represent it as what? Mu. Okay, now the population, let's say UVA-wise now, is the population. Or the total number of students at UVY is, let's see, uppercase N. Let's use uppercase N to represent that. Now, the subset of that is the mathematics and computer science. That's our sample. So the number of students in MCS is going to be small n, little n. Take note of that. And this is a sample. If you are computing sample mean, you use X bar to represent it. If you are computing population mean, you use mu. Therefore, sample mean is actually, you add up all the data points, okay, and divide them by, I think, n minus 1. Where is that? Did I miss anything? Oh, sorry, that's not, sorry about that. You divide them by n. That's just mean. Oh, I'm thinking about standard deviation in my head. And then population mean is just, you add up all the data in the population set and divide it by uppercase N. Okay, look at the notation again. X bar is for sample mean, and mu is a Greek symbol, is for population mean. Okay, so if you have this data set, the mean is going to be 2 plus 9 plus 11 plus 5 plus 6 divided by how many of them? 1, 2, 3, 4, 5 divided by 5. And that will give you 6.6. You see that? Again, this is a sample. This is a sample. Okay? This is a sample. The question says, draw a dot plot for n equals to 5 measurements. Find the sample mean and compare the value with what you might consider the center. Now, if you plot all those, 2 is here as a 2. That is 9 here. If you just spread them evenly, start from 2, 4, 6, 8, 10. So 2 is obviously here, and that is 4 here. That is 5. 5 will be this dot, and that is 6. That is 6. Now our mean is 6.6. Okay, that is this red triangle. And do we have 9? Yes, 9 is around here. Do we have 11? 11 should be here. This is called a dot plot. A dot plot. Now, to compute the mean, you have to add up all these numbers. Now, you are looking at this sigma. This sigma is just a notation. Is a what? Is a notation to mean, hey, add up. So if you see something like this, I equals 1, 2, 3. It means your I ranges, the value of your I is from 1 to 3. I 1, 2, 3. And this means sum them. Sum it. This is summation. So sum up 1, 2, 3. That will give you 6. So that is the meaning of this. Sigma or summation. Sorry. Not even summation symbol. Okay. Now, the mean is quite straightforward to calculate. For instance, if you have another set, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 numbers. The mean of this is going to be X bar equals add up all the numbers, which is Xi over N. Now, if you add up all these numbers, you're going to get 55. And how many of them is 10? So 10. You have 10 of them, that is 5.5. Okay? That is a mean. Mean is straightforward. Now, there's another measure. Remember, we're talking about measure of center. So the second measure of center is median. So the median of a set of n measurement is a value that falls in the middle position when the measurements are ordered from smallest to largest, okay? When they are ordered from smallest to largest, so look at these numbers, 2, 9, 11, 5, 6. So you have to arrange them. You can arrange them from smallest to largest or from largest to smallest. It's the same thing. Okay? So ascending order or descending order. So now, when you look at that number, to the left, number 6 is in the middle. After sorting the number, to the left of 6, you have 2 numbers. To the right, you have 2 numbers. So this is the median. That's how to calculate median. Okay, but now you remember that this is odd numbers, 5 of them. When you have odd items, you don't have to worry yourself. Just sort the numbers, sort them first, and pick the middle number. But when you have even items, there are 6 numbers here. So you sort them first. Accordingly, I can sort from largest to smallest. Let me try largest to smallest. 27, 11, 9, 6, 5, 2. So the middle one is 9. To the right of 9, I have this. To the left, I have this. So, wait. So, sorry, that's a mistake. My bad. So if you have even numbers of items, there are 6 of it. So after sorting them, you can sort, you can sort from largest to smallest. I don't care about that. 11, 9, 6, 5, 2. So you will pick the middle numbers, 2 middle numbers. You want to make sure you have the same number to the right side, the same number to the left side, 2 numbers on the left, 2 numbers on the right, depending on the on the set. Then the one in the middle, you add them up, 9 plus 6, you divide it by 2, that will give you 7.5. Yes, 7.5. Even if you have, let's have another one. 1, 9, 3, 4, 8, 6, 0, 5. How many do you have here? 2. Can you see that? Now, this is number 6. The first thing you do, you sort the numbers. I'm computing the median. When you sort it, it becomes 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you see that? Now, if you count all of, no, is it 9? 1, 2, 3, 4, 5, 6, 7, 8. 7 should not be there. Yeah. So 8 numbers. Now 8 numbers are even. You have to come to the 2 in the middle. So here you have 3 here, 3 here. So 6, 8. So you have to add up 4 plus 9 and divide it by 2 to get 4.5. That is the median. Okay. So now, when your data set is very small or large, the sample mean is drawn towards the direction of the extreme measurements. So if a distribution is skewed to the right, when you see this word skewed to the right, let me draw this graph. It means you have more data to the right side. Right skewed. And if it is skewed to the left, you have more data to the left side. This is a left skewed. See, more data here. That's the left skewed. Now, if a distribution is skewed to the right, the mean shifts to the right. That means the mean is greater than the median. Look at it. If you have this, right? And the mean will tend to be here. Median will be before the mean. That's what it says. Okay? And if a distribution is skewed to the left, the mean shifts to the left, and the median is less than the mean is less than the median. When a distribution is symmetric, look at that word symmetric, the mean and median are equal. If a distribution is strongly skewed by one or more extreme values, you should use median rather than mean as a measure of centers. Okay? If you can use a measure of centers is that what? Mean, median, mode. Okay? Central tendency. So if you have a distribution that is strongly skewed by one or more extreme values, for instance, if you have something like a set like this, 1, 2, 3, 25. For something like this is very big numbers. It is more appropriate to use median to do that. I'm telling you, it is more appropriate. Okay. Now we talk about mode. Mode is the category that occurs most frequently. The most frequently occurring value of X. Okay. When measurements on a continuous variable have been grouped as a frequency or relative frequency histogram, the class with the highest peak of frequency is called the modal class. The modal class. And the midpoint is taken to be the mode. Let's look at that. Look at what we have here. Mode is generally used to describe large data sets. Whereas mean and median can be used to describe both large and small data sets. Does it make sense? Okay. If you have extreme values in your data, it is preferable to use what? Median than mean. And when your mean of your distribution equals to median, then you have what is called symmetric distribution. Symmetric distribution. Okay, now you have a data given here as the hospital visits per week, 5 visits per week, maybe week 1, week 2, week 3, week 4, week 5. Now, 5 occurs most. See, 5 times. 5. So this person visits the hospital 5 times. So you have the frequency for 5 is 8 times. Look at it. 5, number 5 occurs 8 times. 4 occurs 3 times. 7 occurs 3 times, so on and so forth. 6 occurs 7 times. Let's count how many 6 we've got. This is 1, 6, 2, 3, 4, 5, 6, 7. Okay? So this is the histogram to represent it. Remember, this is a relative frequency histograms. Relative frequency is very useful. It's very useful because it can easily show how many times each of them appears compared to the rest. And for the bad weight data, the other table I showed you earlier on, the mode frequency is 7.7. That occurs the most. Let's count it. 1, 2, 3, 4. Yeah, that 7.7, is it 4? Yeah, 4 times. Yeah, that's right. So that's the mode frequency. Now, using the histogram, you can find the modal class. The class with the highest peak. It is the 5th class, which is here. Which is right here. Right? Okay, so mode, it's easy to pick. You don't have to do too much calculation to get the mode, but you have to do calculation for median sometimes and mean all the time. All the time you have to do calculation to get mean. So it is possible for a distribution of measurement to have more than one mode. It is possible, for instance, if this height is the same, if it is the same, this is one class, this is another class, but they have the same mode. That is called bimodal. And you can even have 3 having the same mode. This is called 3 stripes having the same frequency height, the same height. 1, 2, 3. This is called multimodal. Multimodal. So it's possible. Okay? Now, sometimes bimodal distributions of size or weight reflect a mixture of measurement taken on males and females. In any case, a set of distribution of measurement may have more than one mode. Okay? So let's talk about measures of variability. Measures of variability. Now, we've talked about measures of center. Center measures, right? Center measures, which are mean, median, and mode. Now, variability is about spread. It's measurement of spread. For instance, if you have a data given as 4, 8, 9, 31. So one of the measures of spread is called range, which is highest minus lowest. So the range here is what? 31 minus 4, which is 27. Okay? So variability is a very important characteristic of data. So because if you are manufacturing both, for instance, extreme variation in the both diameters could cause a high percentage of defective products. You have a product A, your product A product diameters, and you have 1, 3, 1.4, 1.2, 1. Suddenly you have 10. This 10 is going to cause a lot of trouble. Okay, that's a big variation. On the other hand, if you are using an exam to judge ability of accountant, you will have trouble if the exam always produce grades with little variation. It will be hard to tell which accountant was the best. In other words, now you are looking for best students, and they all have like 71.2, 71.1, 71.3, very close. So it's going to be hard. Now, the variation here is very minimal. In this case, it will be hard for you to make a judgment. Okay? So measures of variability can help you create a mental picture of the spread of the data. And the simplest one is range, which I've just done. Range is does what? Largest minus smallest. And then we have variation of a population. Now, remember population set, which is like a UVA-wise as a whole. Now, there is what is called variance. Sorry, not variance of population. Sorry. Now, when you see a formula like this in math, I've told you the meaning of this is addition, right? Now, all you can see here is subtraction. You are subtracting. You are squaring. You have addition. And you have division. These are the things we all do in maths. Okay? So if you are computing variance of population, you have sigma squared. That's how, so you sum up the differences between each data point and the mean, you square them, you sum up all the differences, and you divide it by the number of items in the population sets. Look at that. Remember, the mu is the population mean, right? Take note of this formula. This is just a notation, okay? Sigma rho square. Now, however, variance of a sample is given as S square equals differences between the mean and each of the points, square them, divided by little n minus 1. This is very, very important. Here, only divided by n. Here, only divided by what? N minus 1. Okay? Now, so the variance of a sample n measurement is the sum of the square deviations of the measurement about the mean divided by n minus 1. The sample variance is denoted as it. Now, this is just a denotation, right? Now, the reason why this n minus 1, I won't talk about it in this class, okay? Just know that you will have set of measurement 5, 7, 1, 2, 4. This is when you add them up together, you have 19. Now, when you compute the mean, you have, I think the mean here is 3.8. So you will be subtracting 3.8 from each of these to get this. Subtract 3.8 from each of these. Now, after getting this, you will square them, raised to power 2 to get this. Then you add up this. Then you will divide the sum of differences, sum of the squares of the differences divided by n minus 1, because this is a sample and n is 5, so 5 minus 1. You have 22.8 over 4, it's 5.7. That is the sample variance. So the variance is measured in terms of the square of the original units. That is why you see, to represent variance, we are using square on top of this variable. The same thing here, sigma square. Okay, once again, population variance. Population variance is given as rho square equals sigma of xi minus population mean all square raised to power, all square divided by uppercase n. Whereas sample variance is s square equals sigma xi minus x bar square divided by n minus 1, little n. So that is what you have there. Okay, and we have what is also called standard deviation. Standard deviation is a set of measurement that is equal to the positive square root of variance. So if your variance is 4, standard deviation is just square root of variance, which is square root of 4, which is 2. Okay? Okay? Now, be careful that you do not confuse the 2 here as a square. It's just to show you that the operation involves square. Okay? So, if your variance is 4, standard deviation will be square root of variance, which is square root of 4, which is 2. You know, square root of 4 is actually plus or minus 2, but you have to pick only the positive one. Okay? So that's the relationship between standard deviation and variance. Okay? Now, This is just another way to represent the formula, but I wouldn't want you to disturb yourself too much on that. Just know that variance is sigma xi minus x bar squared divided by little n minus 1. That is for sample variance. But population variance is rho square equals sigma xi minus mu square divided by uppercase n. No minus 1 here. Take note of that. Okay. And in terms of notation, this is called sum of squares of the individual component. Why this is called squares of sum of the individual component. Remember, x1 plus x2 squared will never be the same as x1 squared plus x2 squared. This is called squares of sum. And this is sum of squares. Okay? So in any case, you'll be given the data. So do not worry about, this is just another way to represent this formula here. That's standard, but this is another way to represent it. Another way to represent it, which is more convenient for a lot of people. Okay? Now, the value of x is always greater than or equals to 0. So your x can never be less than 0. The larger value of x squared means that if your x is big, that means there is a greater variation in the data set. If your variance is 0, that means all the data must have the same value. If your x, sigma square equals 0, that means you have the same data, like 4, 4, 4, 4, 4, 4. That's the meaning. Because if you compute the mean of this, you're going to get 4. The mean of this is going to be 4. And by the time you do your x bar, xi minus the mean, that will be 4 minus 4 square, 4 minus 4 square, you get 0. So if variance equals to 0, that means the data set is homogeneous. It contains the same value all through. Okay, then let's talk more about standard deviation. Okay, standard deviation. Standard deviation. Now, you know how to calculate standard deviation. Standard deviation, it's square root of variance. You have to memorize that. And I've given you formula for computing variance. For population, you have, this is just a notation, sum all the difference square divided by uppercase n, okay? But for sample, you have x squared, you sum all this divided by little case n minus 1. So it's always different. Now you know how to calculate standard deviation. If you can get this, then standard deviation will just be square root of this. Square root of this. So you can even say the standard deviation for population is the same thing as what? Square root of sigma x minus mu square over n. Yeah. Okay, so now that you know how to calculate standard deviation, how can you use it to help describe the data set? A useful theorem developed by a Russian mathematician named Chebyshev gives a lower bound to the fraction or proportion of measurement that you can expect to find falling within certain interval. It applies to any set of number. So Chebyshev's theorem. Now, so far so good. I've talked about mean, median, mode, variance, standard deviation. I've talked about range. I've talked about skewness. I've talked about symmetric distribution. Okay? Right skewed and left skewed. I've talked about that. Now, given a number k that is greater than or equals to 1, like 2, any number from 1 and above, and a set of n measurements, at least 1 minus 1 over k squared of this measurement will lie within k standard deviations of their mean. Chebyshev inequality theorem. Okay, but I don't want you to stress yourself too much on that. Okay, but it's good for you to know it. Look at how you define it. Given a number k greater than or equals to 1. So k is a number, right? And a set of n measurements, at least 1 minus 1 over k squared of the measurement lie within k standard deviations of their mean. So let's do this. There are standard things that you need to know here. So at least none of the measurements lies in this interval. When we say interval, for instance, if you are looking at this closed interval and you're looking at a set of integers, the possible numbers here is going to be 4, 5, 6, 4, 5, 6. Okay? These are intervals from 6 to 4. None of the measurement lies in this interval based on this theorem. 3 over 4 of the measurement lies in the interval mu minus 2 rho and mu plus 2 rho. Remember, this is interval. At least 8 over 9 of the measurement lies in this interval. So you need to know this. Number 1, you will have the value of mu, value of sigma from the data point. So let's consider an example. The mean and variance of a sample having 25 measurements at 75 and 100, right? The mean, x bar equals 75. Variance is 100. So the standard deviation, SD, is going to be square root of variance, right? Square root of 100, which is 10. So the distribution of measurement is centered at here. The Chebyshev theorem states that 3 over 4 of the entire population, of the entire sample, will lie in the interval x bar plus or minus 2s, which is 75 plus or minus 2 times standard deviation, which is 75 plus or minus 20, right? So if you take plus, you have 95. And if you take minus, you have 55. So at least 3 over 4 of the 25 measurements lies in the interval 55 to 95. 8 over, now these things you have to memorize. You have to remember these things. 8 over 9 of the sample population, sample, which is 8 over 9 25, we have to lie in the interval x bar plus or minus 3s. X bar is the mean, which is 75, plus or minus s is 10, which is 75 plus or minus 30. So the interval is what? From 7 plus 30, 75 plus 30 is what? 105. And 75 minus 30 is what? 45. So 45 to 105. Okay, now what is most important here is this 3 over 4 of sample we be in the interval u plus or minus rho. And 8 over 9 of sample will be in the interval u plus or minus 3. No, 2. This is 2 rows, sorry. 3 rows. So you have to remember this 2. That's Chebyshev inequality. Chebyshev inequality. That's the name of the graph. And we have what is called the empirical rule. Another rule for describing variability of a data set does not work for all data sets, but it does work well for data that pile up in the familiar mansion, which is called normal distribution. So the closer your data distribution is to the mansion, the more accurate the rule will be. So we call it empirical rule. See, it's very almost accurate, almost equally, almost symmetric. See that? So empirical rule states that the interval mu plus or minus sigma contains 68% of the measurement. And mu plus or minus 2 sigma contains 95%. And finally, mu plus or minus 3 sigma contains 99.7%. Now, the most important thing is that you must be able to compute your population mean, which is your mu, and sigma, standard deviation, right? Standard deviation. Let's look at it again. Okay, so variance, mean and variance, So that's called empirical rule. So we have 2 things now: Chebyshev inequality and the empirical rule. And why are they useful? You want to describe the measurement. You want to know where most of the data lies. And you want to make decision with that. Okay? So let's see an example here. In a study conducted at a manufacturing plant, the length of time to complete a specified operation is measured for n workers. Okay? So sample size is what? 40. The mean is 12.8 and 1.7. Describe the sample using the empirical rule. Look at that. Empirical rule, you have the mean plus or minus the standard deviation. Okay? We have to calculate the interval. Now, the interval says 68% of the measurement. So 68% of the measurement fall in this interval. So according to the empirical rule, look at that. You remember this will be given to you right here. It's already here. The values are already here. So all you have to do is to what? Look for this x bar plus or minus s, x bar plus or minus 2s, x bar plus or minus 3s. So, and you have them here. These are the interval. So this interval contains 68% of the size. The second one contains 98%. And this one contains 99.7%. So this, I'll go for the third one. I'll go for the third one. So now, but remember, empirical rule assumes that the distribution is almost perfect, like almost symmetric. Or if you are not sure of the nature of the graph, just use Chebyshev theorem to avoid doubt. To avoid doubt. Empirical rule is for what? It doesn't apply to all data, but Chebyshev applies to all data. Okay, so I don't think I can finish all of this. I'm going to stop my videos here tonight, and I think this has been very informative for you.